So in today's lesson, we get to learn what a radian is. Now, a radian is just a way of measuring an angle. Up till now, we've measured angles only in degrees. But there are many things that we do that require more than one type of measurement. So, for example, if I ask Stephen, how tall are you? 6'1". 6'1", okay. Brandy, how tall are you? Okay. So, you're 6'1", and she's 1.64. So are you way, way taller because yours is 6'1" and hers is 1.64? Or she might have told me in centimeters and she could have said 164. And then she would be way taller than you? Well, no. We're dealing with different measurements. You're talking about feet and inches, and she's talking about meters and centimeters. But they're both ways to measure height, right? In North America, when people ask you your height, most people say feet and inches. But when you get your driver's license in Canada, it is in centimeters. You're just going to check now? Yeah. See if your height on your driver's license, is it in centimeters? Because Canada decided to go towards the metric system, but because we were in the imperial system before, we still use a bit of both. In the United States, they only use feet and inches. So now you know how many centimeters tall you are. So a radian is just another way of measuring an angle. So we have to figure out how to compare them, because when we talk about 3 radians, you might not know what is that like. How many degrees is that? I can't picture that because I can't convert things back and forth. So until we get a picture of what is a radian, then we'll be able to figure out how we can change from degrees to radians. So what I'm going to do to help you see what a radian is, I'm going to draw a circle here. I'm going to draw a circle. The center is about there. There's a circle that has a radius about the same radius as this triangle that I'm holding. What kind of triangle is this? It's got a special name. It's an equilateral triangle. What makes an equilateral triangle an equilateral triangle? All the angles are the same. All the sides are the same. Okay? So if I drew that equilateral triangle on here that I just used, it would look like this. And all of these angles would be 60 degrees. And all of these sides would be the same. The definition of a radian one radian is the angle, wow. When this arc right here is the same length as the radius. So if I was drawing that arc, and maybe I'll use a different color. If I was drawing this arc and I needed it to be the same length as that radius, or the same length as one of those sides as an equilateral triangle, would it go all the way to where it touches? Would it be shorter or would it be longer? A little bit shorter. Because in order for it to work, right, it'd be like I'd have to squish this down a little bit to get it to be bent. And if I squish it down just a little bit, that'll change this angle right here a little bit smaller. So if I squish this triangle so that this length here is the same as the radius, that is exactly 1 radian. So this angle right here is 1 radian. If you had to estimate, just looking at that picture, and you were estimating, what do you think 1 radian would be approximately? So I've taken my equilateral triangle, I've pushed it down to get the curve of a circle. This length, the curve of the circle, is the same as the radius's. What do you think this new angle would be approximately in degrees? 50 degrees. So there's our estimate. That estimate is not correct to the nearest 10 decimal places. That's just our first estimate. As we go through this lesson, we're going to see how close we were. Okay? So 1 radian is the angle when the arc is the same length as the radius. If we draw our circle again, and it doesn't matter what size of circle you use, the size of the size of a radian is the same. Bigger or smaller, the amount of distance it takes to travel 1 radius along the edge of the circle is going to be the same angle every single time. So now if I took this circle right now and I said this is my radius, starting from here, if I bent and put one of them here, it would go to about there. If we did another one, it would go to about maybe there. How many do you think it'll take to fill up the whole circle? So we've got one here, another one there, third one will go to about there, fourth one to there, fifth one to there, sixth one will go to there. So if we had a piece of string and actually measured each one out as best as we could say there are 6 and a bit. Now this isn't very accurate yet, is it? 6 and a bit. It's not like you can write that as an answer on your math test. Oh, it was 5 and some. Usually you lose half a marks for being inaccurate like that, right? But there are 6 and a bit radians in a circle. So that's where we're going to have as a starting point. We're going to try and figure out what it is exactly. How do we figure out what it is exactly? How many do you think? If you had to guess an exact number, what would you think? Pi times 2. Okay. That is the exact number. Pi times 2, 2 pi. There are 2 pi radians in a circle. That sounds a lot more accurate and mathematical than 6 and a bit. And it is. But now how do we know for sure? How do we get that number? Okay. Now how do you know the diameter wraps around 3.14 times? Okay. So maybe you remember from a definition of pi that pi comes from how many diameters fit around a circle. Okay. And there are pi, so there would be 2 pi radiuses. Yes? Good. So if we look at our circumference formula is 2 pi r. Sometimes we don't take the time to actually think, what does this mean? If I put a little dot just there, that means that there are 2 pi and r stands for radius. That's telling us, a formula tells us a relationship. The relationship between a circumference and a radius is that it takes 2 pi radiuses to wrap around the circle. And the same thing that another way of writing this formula is sometimes this formula is just written pi times diameter, exactly what Julie said before, is that there are pi diameters around a circle. And so once we have that idea and we say, wait a minute, if every time I have a radius around the edge of my circle, and that's the definition of 1 radian, that means that there are 2 pi radians in a circle. And 2 pi is approximately 6.28. How many degrees are there in a circle? 360. So now we have a way of comparing. We can compare our degrees to radians because we know something that's equal. We know that 2 pi radians is equal to 360 degrees. How much do you think pi radians is equal to? 180. How would you figure out what 1 radian would be? How did you get pi divided by 3? Half of it is pi, okay? Okay. It's not 1 over pi. So let's take a step back here. How did you figure this out when you went from here by here? What did you do? Divided by 2, right? That makes sense? We divided by 2 to get from there to there. How would I get from here to here? Divide by pi. So why do I have to do here? Divide by pi. So now we got to check how close was our initial estimate, because you can type that into your calculator. We now know that 1 radian is equal to 180 over pi, so we take 180, divide by pi. We get approximately, if we round it, 57.3 degrees. So you squished it too much to get 50, but it's not bad. We know that it's a little bit less than 60. Pi is close to 3, right? 3.14. 180 divided by 3 is close to 60. It is 60. So if you divide it by something a little bit bigger than 3, you would get something a little bit less than 60. So we could work that way and get what 1 radian is equal to. We could also work and find out what's 1 degree equal to. How could you use the numbers that are there to figure out what 1 degree is?
1 over 180.
Okay, very close. You went from here and divided by 180, right?
Yeah.
So you have to go from here and divide by 180 as well. So it'll be pi over 180. Because I went from here, divide by 180 to get to 1. So then I'd go from that one there, do the same thing and divide by 180.
Oh, yeah, that's right.
And we got it, pi over 180. So 1 degree is approximately pi divided by 180. You type that into your calculator and you get like a small decimal. Now, a couple things to notice. Notice how with degrees, we always write the degree sign. There is no symbol for radians. So if you're talking about an angle of 2 and you don't write any symbol with it, you are talking about 2 radians. In grade 11, when you were doing math and you might have, maybe your teacher took off half a mark in grade 11 because you forgot the degree sign while you were doing your work. The reason for that is technically, instead of writing sine of 50 degrees, you were doing sine of 50 radians. That's a big difference, because 50 degrees is a little angle. And 50 radians, well, if you think 6.2 radians is once around a circle, 50 radians would be like almost 8 times around a circle. So it'd be very, very different. When they talk about sports in the Olympics that involve turns, right? Like snowboarding. You could do a 1080 in the air, but they're talking degrees. 1080 would be 3 times that you'd spin in the air. If you become the first person to ever do 1080 in radians, that would be like, if we do 1080 divided by 6.28, how many spins would that be? I'm sure you'd win gold medal. Oh. Oh, my calculator's not working right now. There it is. 171, almost 172 full revolutions. You do that in the snowboarding, I'm sure they would give you the gold medal. If you were able to turn 172 times. What is the record? Does anyone know? How many times you can spin in the air in snowboarding? So, anyways, so we get back to this. Now, these last two are very helpful for changing from radians to degrees and degrees to radians. For example, if you wanted to know, if you wanted to change 20 degrees to radians, could you see that if I know that 1 degree is this, 20 degrees will just be 20 times this. So we'll have 20 times by pi over 180. And you could leave your answer like this, 20 pi over 180. Or if you wanted to, you could reduce it. You could reduce that fraction to pi over 9. So 20 degrees is equal to pi over 9 radians. And all I did was multiply by pi over 180. If I wanted to change five radians into degrees, well, I would take my 5, and here on my chart, I'd say, well, I know that 1 radian is 180 over pi, so 5 radians would be 5 times 180 over pi. And if you type this into your calculator, you find out that that is approximately 286 degrees. So for changing back and forth, these two, what you have to multiply by, become very important. Now, a couple things for remembering which one is which. If I'm ever confused about which one is which, I always go back to this chart that we made to start with. Start with what you know. You know that there's 2 pi radians in a circle, and there's 360 degrees in a circle. From that, you could find out that 1 pi is equal to 180. And then you could divide by pi to get this one, or divide by 180 to get this one. And you could derive those and then figure out which one do I need to use. So if I want to find 20 degrees, well, I know 1 degree is this, so 20 degrees will be 20 times that. If I want to change 7 radians to degrees, well, I know 1 radian is this, so 7 radians will be that. The other thing that I use to help me remember is visualizing that triangle. I know that 180, when I squished that triangle, was just a little bit less than 60. So when I think about these two fractions, 180 divided by pi or pi divided by 180, which one is close to 60? And that would be that 180 divided by pi, because pi is close to 3. So that's another way that I help remember which one is which. Now, if you look at the top of page 489, on page 489, they summarize this there as well. They're saying that 1 radian is 180 over pi, 1 degree is pi over 180. They've got the whole circle there, and we talked about how the circumference can help us figure that out. And they've got that pi radians is 180 degrees. What we did yesterday in our math lab is we found out a formula for in degrees for figuring out arc length. Just a little reminder of that. We figured out that our arc length of any angle theta was just whatever proportion of 360 it was, so whatever that fraction was of our circumference, 2 pi r. That was the formula that we developed for arc length of any angle. On your formula sheet, have I given everybody a formula sheet? Yes? On your formula sheet, the very first formula on your formula sheet is for arc length in radians. Now, I don't know why, but they use the letter S for arc length. Arc doesn't have an S in it, so I'm not sure where that came from. If someone can think of a nice word that represents the curve of a circle, maybe if you spell circle wrong with an S, I'm not sure. So I don't know why it's an S, but it's an S on your formula sheet. And if we did the same arc length formula, but we changed to degrees to radians, well, we would still have a proportion. But now our proportion would be out of, instead of 360 degrees, it would be out of 2 pi. And we'd still multiply that by our circumference. But something so easy to simplify happens, right? Here's our proportion of the circumference. Can you see that the 2 pi on the bottom can cancel out with the 2 pi in the formula? And the formula just becomes theta r. Of course, this one here is degrees. And this one, this theta r formula, only works if the angle's in radians. So you have to know what proportion you're using. If you're in degrees, you're going to have to use this kind of a formula, the proportion of the circumference. But make sure that we have theta over 360 because we're dealing in degrees. If we're dealing in radians, we have the same formula, except now it's theta over 2 pi. And our formula simplifies so nicely that we often just write it like this. It's theta times the radius. And I'll just give a little example to help you see why that happens. Let's say I draw a circle and I draw an angle of 2 radians. The definition of a radian says that every time I have a radian, I have 1 radius on the outside of the circle. So if my radius was 10, my arc length would be 10 plus 10, or 20. Now, according to the formula says take your angle, in this case it's 2 radians, take your radius, in this case its length is 10, and so the arc length would be 20. And so now we have a new formula for the arc length.